camera shooting.
So powerful. So yeah, so what we do, we ask the patient to carry some kind of thoughts, not only do become ask them we ask what's the carry. Learning technique. Patient doing alone, that's no helps the
Yeah. So Professor Ramana have mentioned about DELSIS. Okay. So we also have two standees here. Any idea what is DELSIS? Have you at least did a small Google search about DELSIS? Yes, it's company name, but what does the company do? Okay. Okay. So we only manufacture EMG equipments, not even biomedical, only EMG. We are specialized in EMG. Okay. Um, can I show the presentation? It's connected. Yeah. Okay. Till that gets fixed. Um, how many of you have utilized EMG or created your own EMG? Okay. So only one. What's the EMG do you use? Is it your own EMG or some commercially available equipment? Okay, fine. That's an Indian company, right? Okay, fine. So I hope for the last 2 days you had some basics or maybe overview about EMG. I don't want to again bore you with the same stuff. Okay. Um, any idea what are the intrinsic factors which will affect EMG signals? There are two factors which is mainly for EMG. Okay. Some factors are intrinsic, your body's intrinsic factor. Then some factors are like extrinsic factors, maybe like your environment, maybe your power source. Any idea what are the intrinsic factors which may affect the EMG signals which you acquire? Because it's all about sensing, right? You'll be using sensor to capture the muscle signals, right? So what are the intrinsic factors which you think will have effect or impact on EMG signals when you acquire? Sorry, sir. Okay, that's mainly crosstalk. Yeah, yes, that's one aspect. So when we talk, like we are basically talking about surface electromyography. Okay, so we have like a number of like, I think the first day somebody mentioned 600 or above muscles. I don't want to go there. Reasonably speaking, you can go up to let's say 50 muscles as a surface you can capture. So you have muscles in the deep or middle layer as well. So we cannot pick up those signal with the help of these surface EMG sensors. Okay. So as you mentioned, like subcutaneous tissue or fat, whatever it is, what's the depth you think it can capture? The muscle signal, actual muscle signal. Sorry? Yeah. Average 2 to 3 centimeter. Anything beyond 3 centimeter, if I have to go deep, then needle based EMG will be utilized. That's more for diagnostic purpose. Okay, for any control aspect or any rehabilitation engineering, human machine interaction, brain computer, it's all you're just collecting signals from the superficial muscles. Then Professor Ramana explained about the process, like you acquire pre-process, then do the signal processing and everything, feature extraction. End of the day, you are giving this input to a microcontroller. Then that completes the activity. Okay, so ideally you will be working mainly with 30 muscles for rehabilitation engineering aspect, be it lower limb prosthetics or upper limb. That's the major muscles you will be utilizing in practical scenario. I am talking everything from a practical standpoint. If you have, let's assume you have a lab which has EMG sensors or motion capture, force plate, everything. You can like motion capture will provide you kinematics, the camera based or IMU sensor based, which is joint angle, acceleration, angular velocity, gyroscope, those aspects. Then force plate will give you details about the kinetics, which is ground reaction force. Okay. Finally, EMG sensor is the only thing which will give you details about the physiological signal. If my physiology is not functioning properly, my kinetics and kinematics will not be there. That's the output of my internal functions. Am I making sense or is it too hard to follow? Okay. Yeah. So since it's not working, I'll just read out what's in my presentation. There is a how difficult is to measure EMG. Okay. So this phrase was given by our founder. There is also a book called Muscles Alive. The book was written back in like 1985. You can read the book if you are mainly interested or working in EMG. So there is a phrase, electromyography is too easy to use, okay? And consequently, it's too easy to abuse. Easy to use and it's easy to abuse as well. If you know how to utilize EMG, then it will have like lot of impact, because when he did a survey, you all mentioned like EEG 6 or 7, 3, 2 EEG, because that's not user friendly for real world application. Have you seen anybody who is wearing a EEG cap or maybe like wearable EEG for controlling let's say prosthetics or any application? Have you seen somebody outside? Because it will look odd, right? And what's the second one? It's invasive something, invasive. So how many people know about the company which Elon Musk does? So how many participants he finally has in the recent time? I think 11 or 12. Okay. So implementation is very tough in the invasive side. Then I think third one is EMG. Close to 20 people have raised. Why? Sensors usage, non-invasive, and it's easy to use, easy to deployable in real world scenario. Nobody is going to look at what is this, or they will not look at you or stare at you. I'll give you one more example. Have you seen EMG's Meta's neural band? Facebook company Meta, they come up with the neural band. It's something similar to your smartwatch. How many of you know Whoop, the tracking device, sleep tracking? Those are all like wearable devices. So similar to Whoop, Meta has come up with the neural band. So that just sits on your wrist. Nobody is going to bother about it because it's wearable device, right? So that's why EMG is too easy to use and at the same time too easy to abuse. This quote was like mentioned back in like 1997, but I'm seeing the differences today in the real world environment. So coming back to the intrinsic factors, fiber type, muscle fiber types, fiber diameter, blood flow, subcutaneous tissue, lactic acid, motor unit firing rate, conduction velocity. These are the intrinsic factors where we have no control about EMG signals. Okay. Then there are some extrinsic factors which we can control. That's where Delsys comes into play, or any other EMG commercial available company comes into play. Sensor location. Where do you keep the sensor on the muscle? That's more important for the signal you acquire, for the good quality of the signal. For example, let's say I have biceps muscle, and the basic principle of surface EMG is you have to place the sensor on the muscle belly. But in this position, if I assume and place the sensor here, thinking it's muscle belly, but when I actually contract, muscle belly goes up. So it's a wrong placement. Okay. So if I just assumed it, I have placed it here, and I also recorded the data. So whatever the data which I collect, it will contain lot of noise than the actual muscle signal. So you always do the actual movement, look at the muscle belly, then place it. That's where the physiotherapist comes into play. They will be able to help you out in terms of anatomical placements, finding a proper muscle belly. Okay, that's one example I can say as of now. And next thing is the electrical noises, 50-60 hertz line noise. So if I take the sensor towards electrical, let's say even power source, you can see the signal fluctuations. I'll show you in the demo. Then muscle crosstalk. So for muscle crosstalk, there is something important called inter-electrode spacing in the EMG sensor. Let's say you're all engineers. If you can even make your own EMG sensor. Let's say spend 5,000 or 5,000 somewhere. But if you keep in mind the inter-electrode spacing, that will give you reliable signal for maybe like low cost device. You can create your own prototype. So the inter-electrode spacing which we follow is 1 centimeter and it's patented. Okay. Assume if the inter-electrode spacing is 2 centimeter, 3 centimeter, 4 centimeter. Okay. And you have a muscle belly. For example, again biceps. If the inter-electrode spacing is 3 centimeter, that is going to capture from the entire biceps muscle. Imagine the same scenario, the same sensor with 3 centimeter inter-electrode spacing, you are placing it on your forearm. You have muscles adjacent to each other, which is nearby to each other. And the muscle bellies are very small in size compared to my biceps. So you will collect most of the crosstalks. Then you have to spend your time on like filtering those and reducing the crosstalks. That's all like post-processing you have to do. So that's why inter-electrode spacing is important. If you follow any guidelines, again it's outdated, but encyclopedia for EMG is CENIM guidelines. So they mentioned 2 centimeter is needed or they recommended. But maybe like in the coming sessions, tomorrow, day after tomorrow, Professor Ramana will talk about something called motor unit recruitment or motor unit decomposition. It's about you get EMG signal, then you decompose those signal, then get to know how many motor units are generated for a specific movement or whatever the application it is. So that's one of the extrinsic factor again, which you can control. Then movement artifact. So do you think with this sensor any movement artifact will happen? Because it's completely wireless. You don't have even any wired attachments. Any other thing which you think it will create movement artifact? Sorry? Yeah. Okay. Yes. So muscle movement. That's one good question. So how do I place the sensor on my muscle belly? I need some thing to place the sensor on my muscle belly, right? Then only the conduction also will happen. Typically, if you look into the market, people will either use gel electrode, correct? Or they will be using patch electrode for the conduction. Okay. So we will be using a double-sided medical grade sticker. Okay. It just stays there. It's dry electrode based technology and it just stays there. So you don't need to worry about movement artifact even when the muscle is moving. But if you think about gel electrode, if the gel gets split or spilled away, then you cannot, again, the conduction is not happening, you will not get the good quality signal. So these are the things which will help you in terms of selecting a proper EMG sensor. Maybe you create your own prototype. So it's not opening. Yes, I mean, the muscle is moving, but mhm. I didn't get your question. Repeat. Right. I don't have a port in laptop. அந்த சின்ன போர்ட் இருக்கும் அதை எடுங்க ஒரே நிமிஷம் yeah, so just quickly I'll recap. So these are like couple of intrinsic factors which you have no control, which will affect your EMG signal. These are like couple of extrinsic factor where you can control with the proper sensor designing and interelectrode spacing, those other aspects. I think this is yeah, this is what I was talking about in terms of placement of the sensor. So if you place the sensor on the muscle belly, the signal which you capture, but assume if the sensor on the origin or insertion or during like along the tendon lines, then the signal will be like majorly reduced in terms of acquisition. Then for any EMG, be it dry electrode, gel based electrode, patch electrode, whatever it is, Skin preparation is mandatory to collect good quality signal to acquire. And yeah, if there are a lot of hairs, then you will have to remove the hair. That's it's a practical limitation. It's not a problem, but it's a practical limitation with any EMG you use. Um, why, as Dell says, we are only interested in EMG? I already explained this in the beginning itself. It's about the internal stuff which will help us in completing the external movement or external activity. So that's why we wanted to be in the forefront of physiological aspect, but EMG basically used in physiology as well as biomechanics. You are just computing those results. So it's I just show this mainly to highlight we as a human we are all complex in nature, be it walking, running. Let's say think about the same thing for a patient. He's even struggles to walk, even to take a step. But we are all like free birds, we are working completely fine. So that's how complex the human is. So like it's all basics. I don't want to go through, but if you are interested, like it's almost like 30 years now, 35 years now. That's how we evolved over the period of time. We started as a commercial company back in 1993. Then that's all the product portfolio over the period of time. So this is the current system which we have. You can see it right here. This is the receiver. And these are the varieties of EMG sensor which we currently have. Depending upon the use case, it's all like mix and match. The one sensor which I have it on my forearm, that's the one you see on the first, Trigno Avanti. That's the commonly used sensor for any gait application, biomechanics, or any big muscles of the body. But if you are working on somebody below elbow prosthetics, okay, then you would be mainly focusing, let's say, Trigno Mini, Duo, Quattro, those sensor variety, because that has a precise placement of sensor compared to Trigno Avanti in terms of the muscle belly size I'm talking about. Then Trigno Galileo and Mace, those are like high density EMG systems. I'm not sure if Professor Ramana will cover those, but first we need to understand what is EMG, then we can go into high density EMG. But just to give you an idea, Trigno Galileo is mainly used for motor unit decomposition. So their interelectrode spacing, you remember we talked about 1 centimeter is what we use, but commonly advised is 2 centimeter, as in the standards. Lesser the interelectrode spacing, the more dense signal you collect. Then you can decompose and get to know the intricacies. So Trigno Galileo is mainly for motor unit decomposition. Trigno Maze is mainly for the spatial mapping. Rather than a single muscle, you collect region of muscle activity. And these are like couple of product ecosystems. Like if somebody is interested in biomechanics lab or bionics lab, so we can support with that. Let me directly go into the applications. Yeah. So mainly where all we as Delcis have customer bases, or where they will usually use the devices. Mainly in the research aspect, applied research, then education. And what are the main application areas? Engineering, neurophysiology, biomechanics. These are the three main verticals which we like serve to. So today's like that's what the workshop topic is also. Where do you use EMG? So I'll keep it very simple. EMG you can use it in two ways. One, you use it to validate your device. Then you use it to control the device whatever you are creating. Two application. One validation, other one is control. So where all you can use upper limb and lower limb prosthetics, wearable robotics, musculoskeletal modeling. Some of you have attended the last event, the same video, but for all the new people, yes, it's in one of the facility in German. The individual is a para-Olympic athlete. So he's been put on a powered ankle, below knee and ankle prosthetics. So in this case, we are specifically picking up signal from the unaffected side. So this is, if you are interested in digital twin or musculoskeletal modeling, I'm not sure how many of you are aware about MyoSuit. It's a physics-based simulation platform, open source. You can check it out. There are a couple of competitions also going on by MyoSuit. This is mainly using EMG as a validation. That's cable-based exosuit, mainly for occupational workers. It's again one of the close application which Professor Ramana was talking about, like using haptic-based gloves or cyber gloves along with EMG. So if somebody is interested, these are like couple of publications available. If you want to give it a read, then these are the open source resources which is mainly built on Delsis materials. These are like our users, they are built for the benefit of the society. So like if you just want to have a data to work on your project, yes, you can go through this. Then mainly on the human machine interaction aspect, like how do you use EMG? Like in terms of pattern classifier, then intent detection, then shared autonomy. These are again use cases. I don't want to go in detail because of the time. Yeah. So it's one of the application where the patient is in the initial stages, he's completely bedridden. The EMG sensor is put on his the forearm and wrist component on the red color which you see. Come on, right here. The EMG sensors are placed there. So at end of the video, I don't have the full video of it, but that's a 3-minute video. You can even find it on either YouTube or DLR website itself. Um, they have created actual product out of it. The individual came to wheelchair. On the wheelchair, they fitted the cobot for the day-to-day life activities. Sorry. I'll just fast forward it. So this is again one of the application where when the athlete is, I mean, the individual is going into fatigue, there is some threshold being value set. So once the threshold is hit, the cobot is taking over the job of an individual to assist him. So this is another application comparison of like lifting task. Like it's all those assisted devices or exoskeleton. It's not main. There are many use cases. One aspect is rehabilitation aspect. Then you can also use this to augment, be it let's say soldiers or healthcare workers. You can also do that. That's the application here. The exosuit is augmenting the individual. This again one of the applications similar to teleoperation. Yeah. So this is mainly on the prosthetic control aspect. So it's just mimicking the, but again, these are like very old videos. The latency has been reduced significantly. Yeah, again, couple of publications. And these are like open source tools, mainly if you are into pattern recognition or prosthetic control for upper limb. Then libEMG is a open source toolbox available. And I think Professor Karthik sir will also talk about Nina Pro datasets in the coming session. So yeah, EMG also has applications in extended reality, like virtual reality, augmented reality, but I don't want to go there. We'll directly show you the demo. In the previous session, Professor Ramana was showing about the EMG signals, right? I'll just show that. Then I'll wind up the session. But if you would like to see the sensors, you can always come here and look at the sensor. After my presentation is done, let me add. So in our sensor, we don't have any switches to turn it on. So it's completely sealed by manufacturing. Again, the reason being to give good quality data. If the sensor has a opening and my even sweat can go inside and it can affect the signal quality, right? And to prevent that, we have completely sealed the sensor by manufacturing. So the whatever the sensor which we options provide, it all has a inbuilt IMU. So you can pick and choose what data you would like to see, or maybe like you can record, collect. So I'll just go with EMG and IMU data. I'll just show it as a preview. But before we get there, this receiver has a slot capacity of 32. Okay, which means you can use 32 of these sensor, providing access to 32 muscle for a full body. You can think about in those scales as well. If I have to give you more information, in India we have only like 5 clients who have complete 32 sensor. But in India I have like 200 customers who start with minimum of 2 sensor, that's a separate device. Then they gradually upgrade. But if they have the system, they minimum have 4 sensor, then they keep on upgrading, or any combination of sensor will work with the same receiver. Let's preview the signals. Let me scale it. So what you see right here on the green one, that's completely an EMG signal. Okay. You can call it a resting potential, or maybe I'm not doing much of activity. But when I start contracting, so what I'm doing is nothing but just flexing my wrist. You remember Professor Ramana mentioned like you make a fist as much as possible. You see the difference? Because it just making fist, and I'm also adding another movement. So you from here you collect the data, I mean record the data, then you export it. Then whatever Professor Ramana was talking about, the time domain and frequency domain, time frequency domain, that's all comes in the data analysis software. That's where you will be doing that. Um, I'm not going to go there because it will take much more time. But yes, basically used to calculation scripts already Professor Ramana have covered, so I don't want to again go there. I'll stop my session here, but if you have any questions, I can take it. Okay, so the receiver has a range of like 40 meters, and we are stress testing for 50 meters as well. So that's the maximum available in the market in terms of EMG. Other devices, it's about 20 or 30. That's where they belong. Sorry, like you can keep it in a like inside a lab or even outside. So the maximum is 40 meters. The range. Yeah, that's a good question. So ours is the proprietary RF protocol. Okay. So we collect the signal in terms of only 4 frequency sets. I can even show it. Yeah, you can see the frequency set A, B, C, D. It's all preset frequencies. Let's say like you, even a Wi-Fi signal can alter this signal, but it will not be the same case with Delsis if you are using it, because it's a predefined frequency set. You collect the data in a one single frequency for 1 hour, 2 hour, 3 hour. There are no other frequency sets which will interfere, but there are others available who use frequency hopping protocol. Every time they change, keep on changing protocol, that's where the noise also will come into play. So it will not affect, because we have even tested in high environmental, let's say some factory setups, automotive, um, some hazardous environmental as well we have tested. I cannot disclose, but yes, it's being tested in many like complex environments. Any other question, or you're all okay, clear? Okay, thank you so much for your time. Sorry. Okay, I cannot discuss the cost right now, but I can only say as an individual, nobody can buy your device. Okay, I'll keep it that way. As an individual, you cannot buy it. As an institutional, as a research lab, or as a center, you will be buying our product. So we are actually in the premium side of research market, not in any of the consumer grade level. We are not like some smartwatch which you can buy. Does it make sense? Thank you. Yeah, if you want to see the sensors, my colleague will be here. You can have a look at the sensors. Thank you so much. ஸோ நீங்கள் எல்லாம் சிஸ்டம் எடுத்தாங்க வச்சுக்கோங்க.
Now we can have tea outside. Okay.